Hi, and welcome to part 2 of this series of videos where I am modeling the Umbracal building by Santiago Calatrava in Valencia. In this second part, I would like to mimic what we did in the first one, where we only used vanilla, simple Grasshopper components, but this time I just want to implement the exact same logic within a C-sharp scripting component. I think this is a really good exercise if you want to know a bit more and get more exposure about how to do these things at a lower level and how all those Grasshopper components are actually implemented using this thing called Rhino Common, which is the library, the geometry library that runs underneath Rhino and Grasshopper. This exercise will be very useful for you if you're trying to learn things such as, for example, how to customize your data tree structures, the ones that are coming outside of as an output of the component. If you want to learn more about, for example, how to create a complex like a sweep around the rail with variable sections, how to go back between simple structs and nerves curves geometry, and a lot of other small features that we will have to do to implement this code. It's gonna take a little bit of time to break down because I really want to explain everything that I did here. But you're invited to follow me along, and otherwise remember that there are links here in the description to the source code that I will be using in case you want to have it on the side. Um, and um, and that's pretty much it. Let's get going. Wonderful. So let's get started. Before we start, I would like to recap on what we did in the last video. So if you remember, what we did was we implemented with vanilla Grasshopper the structure of the building, and we started off. The file that you can see here is not exactly the one that I had from the last video. This is the one that is already been cleaned up and grouped and is a bit more legible. And here we started with a bunch of parameters. So the width, the height, the dimensions, like a lot of other smaller dimensions that correspond to a breakdown of the process that we were going to follow. So what is what dimensions are affecting the shape of each one of the parts of the building. So if you want to learn more about what each one of these parameters and each one of these information that we're going to be using for the model, please feel free to go back to the previous video, because in this one we're going to start right away. We're going to start implementing the process in a C# with a C# scripting component and using Rhino Common. So I guess what I'm going to do is I'm going to place a C# script component here, and I'm going to start changing all the inputs so that we mirror what we have here in the parameters. So I'm going to start. I'm going to do this manually. So if you want to fast forward, I'm just going to be like, this is going to be the width. This is going to be the height, and then I'm going to start adding more parameters here, like a lot of them. This is going to be a big component. So this is going to be D, this is going to be H1, this is going to be H2, this is going to be the offset, this is going to be the number of ribs, and remember that here you cannot, in the input parameters, you shouldn't be using white spaces, and that is also in C# is a convention that the variables are named in camel casing. So first letter is always lowercase, and then any consecutive word is uppercase. But here inside of the Grasshopper world, things change a little bit because we usually use like one letter denominations for input variables, which is not great practice in general when you're writing real production C# programs, but whatever. So for example, here lowercase w and uppercase w in a real program could lead to a lot of confusion. It's not great practice, but we're just going to do that for the sake of mirroring what we did in the previous video. So MD2, MW, and if you need to refresh yourself about what these parameters were, feel free to check the previous video that is probably linked somewhere here in the description, etc., etc. Okay, and I'm going to go back and I'm going to start setting what kind of values, what kind of types are each one of these. So, for example, W is going to be a double. They're mostly going to be doubles. So D is also going to be a double. They're all going to be doubles except for example, the number of ribs. And so number of ribs is going to be an integer because we don't have decimal part. Number of spans is also going to be an integer, and then the rest, all of these are going to be doubles. So here, double, MD1, double, MD2, double, MW is double, and pipe radius is double. And if we double click here, we can see that we have a really large double. All the parameters are now the inputs for the function, and I can see that all of them are doubles exactly, and I have one output which is A, but I forget exactly what I did, so I'm just going to start adding outputs as we start programming this component. So now that we have our platform, we have our C# script component, I think we are ready. I'm just going to plug everything in now. I'm going to start plugging everything in here. Number of ribs, number of spans, dimensions D1 and D2. Now MD1 and MD2, the width, and the radius of the pipes. Okay, and I think we're ready to go here. So I'm just going to turn off the rest of what I had here, and I'm going to start working. Oh, I need the base point. I forgot about that. Yes. So base point, and this is going to be this one. And if you remember, this has to be of the type point3D. Okay. So I think we're ready to start. So let's get to this. So the first thing we're going to do is just like we did in the previous video. The first thing we're going to start is by taking the base point, which is somewhere there, and we're going to create the 3 points in the top and here, this one and the other one top. We're going to create the arch, and then we're going to replicate it however many spans we have in the definition. And then we're going to pack all of that into a list, and we're going to spit it out from the component. So that is going to be here. So I'm going to double click here, and I'm going to start by taking the base point here and creating, like we have in the diagram, creating 2 other points and then creating an interpolated curve through them. So we're going to do that here by saying, and I'm going to add a lot of comments because it's going to be a long code, so we want to keep things tidy. Create the first arch. So we're going to have base point, and I'm going to call this arch top point. I'm going to do this a lot. I think I'm going to write very long names because it's going to get messy. And we're going to say this is going to be base point. This is going to be the same point. How are we going to do this? I'm going to create a new point. I'm going to create a new point 3D, which is going to be equal to the coordinates of base point x in the x direction. That's the same coordinate. In the y direction is going to be y plus half the width of the span. So that's going to be base point y plus the half of the span, so 0.5 times the width of the arch, and then on top is going to be the z of the base point plus capital H. So that's going to be base point z plus capital H. Okay, and then similarly I'm going to create the other point, the one that's the other base of the point, and I'm going to do something similar. Be careful with copy pasting. I keep saying this all the time. I should not be doing it myself. Arch top point, arch base 2 point, for example. These are terrible names I'm coming up with. So this is going to be full width, and this is going to be the exact same height. Okay, so now that we have the 2 points, let's create an interpolated curve that is going to go through them. So I'm going to look at create interpolated curve, create interpolated curve, exactly. And I'm going to look at what is it going to take. It's going to take a list of points and the degree, and it's also going to take the knot styles. I don't think we need any of that, so we can just do a list of points and the degree. And because it needs a list of points, so maybe it's actually better if instead of having individual variables for each one of the points, what we do is we actually create a list of points. So I'm going to rewrite this, and I'm going to create a list of points 3Ds that is going to be arch points, and I'm going to start this new as an empty list, list of point 3D objects. Okay. Now the first one that I'm going to add is the one on the base. So arch points. Let's add the one on the base point. That is the one that was coming from the outside. And then these guys, instead of declaring them as variables and giving them names and stuff, we can just create them on the fly and add them directly to our list. So look at what I'm doing here. I am replacing the variables by just saying I'm going to add a new point that is going to be the one on the top, and I'm going to add another new point that is going to be the one on the other end. I'm missing parentheses here at the end, and also keep in mind that in this case, because we need the points to be ordered for the curve, it's very important that that we create these points and we add them to the list in the order that we want the curve to follow them. Okay, so here, now that we have we can create a interpolated curve out of a list of points. So that's going to be the arch points. And the degree is going to be 3, which is it's a very common degree for a NURBS curve. But we have to remember to curve arch curve is going to be equal to this thing. We have to remember to store the result of this operation somewhere. Okay. Just for the sake of seeing if we're doing okay, let me output this from this component here. It looks like we're executing this. There's no error. It's really good practice when you're doing C# scripting in Grasshopper to plug a panel to the out so that we know if things are going well. And here to the A component, you can see that I have a planar curve. I'm going to plug in a geometry box so that we can see it render in the viewport, and I can see that this looks good to me. And if I lower this down, I have and this goes up and down, so things are looking good on this end. Okay, so we have the first arch. So now let's take this and let's replicate it then a number of spans. The next step that we're going to follow is we're going to take this arch and we're going to create copies. We're going to create as many as spans we have in this definition. The thing is that the process that we're going to follow is a little bit different, because when we did it in vanilla Grasshopper, the only thing that we did was we moved the original arch by a series of vectors with increasing lengths so that it was like farther and farther away. And because of the nature of the visual programming environment, that implicitly created copies of that original arch. However, in C# scripting, we can't really do that, because if we take this original arch and we move it, we're actually going to be moving the whole arch. So we're not going to be able to create copies. So we need to actually explicitly make those copies and then translate them or move them however far away we need. So let me show you how to do that. So we're going to start here. And now that we have our first base arch, what we want to do is we're going to create all the arches. Well, for that, we probably want to start off a list, and this list is going to contain curve objects here. And now what we want to do is, because we want to perform this operation of like copying the curve, cloning it, and then moving it as many times as spans we have. So we're going to do this. We're going to create a for loop where we say for however many times starting at 0 and however many times, that's going to be, what is it going to be? The number of ribs. I think that's what we said. And let me see if this is true. Yes, I don't get any error. So however many, I'm going to make this a little bigger. I always keep forgetting to make it bigger. Yes, so however many ribs we have, what I would like to do is I would like to multiply, I would like to take I would like to create a copy of the arch. So I'm going to call this clone, and I'm going to say take the arch curve and create a duplicate. So duplicate this curve, and you can see that this takes this curve and creates an exact copy that I'm going to call clone. And then it's this clone that I want to move a distance away from its original base, the original arch curve that I created before. How long? Well, for each one of the arches is going to be the position of that arch. So the first one, the second one, the third one, the fourth one, times the span of the distance between spans, which I believe in the diagram we named D, capital D. So which means that I can compute that as a value. So I'm going to say distance is going to be equal to where we are, so I, so the first, the second, the third, times the capital D, which is the length of each one of these spans. And then we can say clone translate, and we can see that translate takes either a vector or it takes x, y, z. I want to move it in the x direction, so I'm going to say, can you move it an amount of distance in the x direction, and then 0 and 0. And then once that is done, I want to take that arch and add it to my list. So that's going to be arches. Sorry, I'm going to take the clone and I'm going to add it. No, sorry. I'm going to take the list and I'm going to add this one element, this clone that I just created. Okay? And let me see if we can output that. I'm going to do arches. I'm going to output this here. And you can see that now I have all these replicated elements. Ooh, that is a lot. Oh no, sorry, I did number of ribs, and it's not number of ribs, it's number of spans. Exactly. Number of spans. Okay, and you're going to notice that there's something that is not correct. And let me show you. If we do 3 spans, we actually don't have 3 spans. We have 3 arches, which basically means we have 2 spans. And this is not entirely correct. It's not entirely correct because we always have one additional in the case of the arches, we have one additional arch extra on top of the number of spans. I made this sound very complicated, but basically we have one more arch than spans. So here I can just say +1, and then now that we have 3 spans, we have 4 arches. So now this makes sense. Okay, and before I start doing anything else, I want to start being a bit cleaner about the outputs that I'm spitting out of this component. So what I'm going to start doing is I'm going to start creating explicit outputs. So here, for example, this is going to be arch curves, which will be different than the arch surfaces. And I want this one to be the one that is going to output, for example, the arches. So what did I call this? Arch curves is going to be arches. I'm going to output that. So that's going to be great, and that's working already here, all those planar curves. And something that I personally like to do is creating like one output that I use to just output geometry and like while I'm developing to see things working. So I'm going to call that here. I've been using A, for example. I'm going to call this the console, just because I do a lot of programming, and so I come from that world. And the console is basically going to be this place where I'm temporarily just like outputting things so that I can see if they're working, whatever. And once they're done, once they're good, then I can output them on the right output, which in this case, for example, was arch curves. Okay, so this one I'm going to pipe it here, and this one you can see that it's already coming out from the component. Okay, so good. The only thing that I would like to add is that you can see that because we created a list, all the elements, all the arches are coming out as in one flat list, so one after the other. And this is okay probably for the arches, it's probably okay for a lot of the other elements that we're going to be generating, but it may actually get messy when we get, for example, to the ribs, because then we're just basically going to output like a list of like hundreds of these ribs. And something that I would like to do for this exercise is to output a cleaner data structure, something that tells me per span which elements do I have. So what I would like to do is I would like to turn this output, which right now is a flat list, I would like to turn it into a data tree, and each one of the branches containing each one of the arches. This will be a little redundant for the arches and etc. But when we get to the ribs, it will actually be really helpful. So because I don't want to do it just for the ribs, I want the structure to be symmetrical across all the outputs. What we're going to do is for each one of the outputs, we're going to output them as data trees. And that's something that we're also going to be using just for the sake of learning. So, let's get together to do that. Cool. Now let's get to it. What I'm going to do is I'm going to transform this. Right now we were outputting a flat list. So what I'm going to do is instead I'm going to create a data tree of elements, and this is going to be curve elements. And I'm going to, sometimes the autocomplete, I'm going to call these arches, and this is going to be a new data tree. Sometimes autocomplete plays games, so I'm going to just do this, okay? And I'm going to remove the flat list, and then what I'm going to do is we're going to do the same process. So we have the data tree. We're going to create the clone curve. We're going to compute the distance. We're going to move that curve, and then before add it to the tree in its own branch. So what we're going to do here is first we have to design which branch this is going to be, this particular arch is going to be in, and then once we do that, then we have to add the arch to the data tree in that particular branch. So the way that works is we can create a Grasshopper Path element, so that's going to be called path, and this is going to be new Grasshopper Path. And as you can see here, the options are basically whichever path, the index, or however many indices you want to have. So for example, I think what we're going to do is we're going to output a simple data tree that goes from 0, 1, 2, 3. The branches are 0, 1, 2, 3 for each one of the arches. So I think with the index number, we're going to be fine. So we can, for the index number, we can just use the value of I, so where we are in that list, the first element, the second element, the third element. And then when we say arches, can you add this element? So what is the element? Okay, if you guys can see here, it tells us that what is the first parameter is which element we're going to add, so that's going to be the clone curve. And the second one is we can specify which path, which branch do we want to insert this element in. So that's going to be path here, okay? And now if we try this out, let's look at how this changes. If I execute this, the magic here is that now instead of a flat list, we have a structured list where each branch contains one of the arches that we just generated. Again, this might feel a little redundant for what we have so far. We could have just grafted this output, but this will show its benefits once we start tackling the most complicated elements, which are going to be I'm gonna call it the ribs. Okay, so all right, awesome. What is the next thing we're going to do? We're going to create the arches, the elevated arches that are here in the middle. Okay, let's get to that. just a quick refresher. Remember that the parameters that we chose to name this were h1 was going to be how high was the starting point of the middle arch from the ground plane, and then h2 was going to be how elevated was the top of the arch from the base main height. So basically the height of this point of the elevated would be capital H plus H2. Okay, so that's the logic we're going to follow here. So very similar. Let's do just like we did before. I'm going to create here, create middle arches. So the first thing that I'm going to do is I'm going to create one base arch, and then I'm going to clone it like we did for the ones in the for the base arches. So I'm going to create a list of point3D objects with list of point3D arches. I'm going to call middle arch points, and this is going to be a new list of point3D objects, and I'm going to copy paste this here, and then for that one I'm going to say I'm going to add here, I'm going to create a new point3D, and let's break this down. The x coordinate is going to be the same x coordinate as the base point plus half d. Okay, so this is going to be base point x plus 0.5 times d. Okay, now the y is going to be whatever base point has for, no, y is going to be the same as, in this direction, y is going to be the same as base point. So what I'm going to do is base point dot y, and then the z coordinate of this point is going to be whatever the z coordinate of the base point was plus h1. So that's going to be here is going to be base point z plus h1, which is a parameter that's coming in from the component. Okay, so that's the first point. The second point, I'm going to do some copy pasting here. Remember, copy pasting is super dangerous, so I'm going to fill in here manually so that I know that everything is correct. So what is going to be the x coordinate? The x coordinate is going to be, like we had before, is going to be equal to whatever base point is. No, it's going to be, the x coordinate is going to be the same as the point that we just did. So that's going to be base point x plus half d. Okay, that's one thing. Now the y coordinate, what is the y coordinate going to be? Y coordinate is going to be equal to the coordinate of base point plus halfway through the width of the arch. So that's going to be base point dot y plus 0.5 times the width of the arch. And then z, which is the tricky one, is going to be equal to whatever base point has for a height plus the height of the arch, so capital H, plus the additional height, which is h2. So as we do that, it's going to be base point dot z plus h plus h2. Whoa. What's going on? Oh, okay, h2. I think we're good. When lines get too long, sometimes it's common practice to break them down like this, and so this is a common thing. This makes code a bit more readable. So maybe we want to do this for all of them, and then the third point is going to be the point on the other end. So this one, we can probably do. I can probably do a little bit of copy pasting here and filling in the blanks. So here I'm going to say base point x is going to be equal. What is x going to be? X is going to be equal to, the x coordinate is going to be the same as all the other points. So that's going to be this. That's going to remain the same. Y is going to be equal to whatever the base plus the full width of the arch. And then base point z is going to be equal to the z of this point is going to be equal to the base point plus h1. So the same as the initial point. Okay. And then now let's see if we can create curve. This is going to be arch middle curve, and then I'm going to create an interpolated curve through the middle arch points. And I'm going to spit out in the console. Remember, the console is just this this fake output that we're using just for debugging and for development. We're going to output this, not the middle arch points. You see, this is arch middle curve. And as we do this, I'm going to run this, and you can see that I have here, I have the arch, and it looks like if I have a view from the right, these are aligned, these are aligned. If H0 is 0, then there's no over anything here. If this is 0, then the points are also on the ground. So I think that makes sense, and I think this looks good to me. Okay, so let's keep working on this. So now we have the middle arches, and what we want to do is we want to do the same thing we just did before. We want to create a data tree, and we want to add, for each one of these spans, we want to create a clone. We want to translate that clone, and we want to add it to the branch. I'm going to write this manually. Data tree, well, maybe not so manually. I'm going to copy paste a little bit. Data tree, middle arches is going to be blah, blah, blah. And then I'm going to create a new for loop where I'm saying this is going to be equal to 0, I is going to be less than the number of spans, and this is just going to be the number of spans because we have the same amount of middle arches as the same amount of spans. So here we're good. I++, and then as we do that, then we're going to say I'm going to clone the curve. That's going to be middle arch middle curve, duplicate curve. Okay, and then I'm going to calculate the distance. Lower distance is going to be I times D, capital D, and then I'm going to take the clone and translate it, that distance in the x direction. So that's going to be distance 0 and 0, and now we're going to add it to the path. So we're basically going to copy and paste here. We're going to create a new path with the index value of which one of the curves we are in, and then we're going to take to the middle arches. We're going to add that clone that we just generated in that path. Okay. As we run this, nothing happens really because we don't have an output. So I'm going to say middle arch curves. I'm going to create a new output here, and I'm going to rename this a little bit. I'm going to say base arch curves. As I do that, if I run this, things are going to crash probably. So I think I want to reopen everything here and now say here we just renamed this base arch curves, and then here we want middle arch curves is going to be this variable that we just created here, middle arches. And let's see if that works. It looks like we have something here, and I'm going to plug a component to see, and I see that I have a nice data tree structure with first element, second element, third element, and they're showing up here. H2 is terribly large, so I'm going to lower that down a little bit, and it looks like it's working. So nice. So I think we're done with the base arches. I think we're ready to move on to creating the ribs. Okay, this is going to be super interesting. If you remember from the previous video, the way we did the ribs was by defining this variable called offset, and offset was the vertical distance at which the ribs started and from the main arches. Okay, and then we only need to do this for the main arches because the ribs started right at the beginning of the middle arches as well. So is this offset, is this distance that we need to compute. And if you remember from the last video, what we did was we created a horizontal plane at that distance. We computed the intersection of that plane with the main arch, and then we found the parameters at those intersection points so that we could create subdivisions of the subcurve that starts in those offsets, and then join those with the subdivisions of the main arch. So we're going to follow a very similar process. So what I'm going to explain first is how to split the main arch given the parameters. And then after that, we're going to find what are the parameter values that we actually need based on that intersection. Okay? So the way we're going to do that is I'm going to go here and I'm going to say, first of all, what I need to work with is with the main arch. And that was, we called it before, it was arch curve. And then what I need to do is here, I need to say, let's compute the sub curve for main arch. Okay. So what I'm going to say is here, if you go to, we were looking at this before on the stream. So the curve class in Rhino Common has a method called split. And what split does is that it divides that curve at a specified parameter. And remember, parameter is this value that goes from usually 0 to some other number, which represents how far along in the curve we are, but it's not Euclidean in a NURBS kind of polynomial way. And then what this method does is, given a one single parameter, it returns an array of curves which are divided from that one parameter. We have another version of this which is given a list of parameters. So given a list of different parameters, it returns the chopped curve. It returns an array of curves, chopping the original one in those parameter points. So I think this is a pretty good one that we're going to use. So what I'm going to say here is I'm going to create a list of doubles. I'm going to call this splitting parameters, and this is going to be equal to a new list of double objects, and to this I'm going to add, for example, I'm going to add two dummy variables. I'm going to add, for example, the value of 0.2, and I'm going to add the value of, I believe the curve that we just generated goes from 0 to 2 as a domain. So I'm going to divide it at 0.2 and at 1.25. Oh, and I forgot, yes, sorry, I forgot to change. And then, so I was here, what I was saying is, I'm going to take this, I'm going to create a list called splitting parameters of doubles, and then I'm going to add two dummy values, 0.2 and 1.25. Okay, and then I'm going to take the base arch curve here, and I'm going to split it. I'm going to split it by using this list of parameter values that it's just a dummy one that I'm creating for the sake of explaining the concept. And if you remember, split returns an array of curves. So you can see here, splits is going to be this one. It's going to be the return of this function. And just for the sake of visualizing, I'm going to output this array of splits to the console output, the one that we're using just for debugging. I'm going to turn off the visualization of the main component, and you can see that we have one curve. Okay, it looks like one curve, but actually internally is here. It's actually three curves that look so continuous because it's just splits, right? And if I actually place here a domain component, we can see that for each one of those curves, the domain is 0 to 0.2, because the original curve went from 0 to 2. So 0 to 0.2, 0.2 to 1.5, it would probably be somewhere here, and then 1.5 to 2. So if I bake these curves, you can see now that I have this one here. You can see that I have this one here. You can see that I have the other one here. And you can see that I have the other extreme here. So these are the three curves that I have split. Okay? So this is great. And then what I would like to do is, I would like to split the main arch into three curves splitting it at some parameter here that is calculated based on that offset distance, and then only keep the one in the middle. Okay, so I can go back here, and then right now what we are doing is we're just splitting the curve based on two random values that I just came up with. But if we want to make this well according to the original design, what we need to do now is we need to calculate for a given offset, for a given vertical distance, what is the parameter of the curve at that vertical distance from the ground. And the way we're going to do that is by chopping the curve with a horizontal plane that is at that height, and then that intersection will give us the parameters at the curve that the intersection has been computed with. So let's try to do that. As usual, before we do anything, we probably want to do some research and some documentation on how to do a plane and curve intersection. So I've done my own research in parallel, and the way you research these things is very basic. You go to the Rhino Common API and you say, let me find an intersection between a curve and a plane. And literally the first thing that pops up is intersection curve plane. So we have that. And we can see that this is a static method, intersection between a curve plane, that belongs to a slightly different namespace than the one that we are used to. We usually just work with geometry objects that belong to Rhino.geometry, but all the intersections belong to a particular namespace, so we will need to take a little bit of care about that. But then we will need to reference that namespace in our component. But aside from that, everything else is going to be super straightforward. For example, we have curve, we have plane, and we have a tolerance for computing that intersection. And you can see that the result is not points or parameters, whatever. It's this thing called curve intersections. Curve intersection is an abstraction that Rhino Common gives us so that we can, and that it encapsulates a lot of the information of why and how this intersection has happened. So for example, a property is count, which is how many intersections did happen. And the other one is item. An item, it gives us access to each one of the intersection events, so each one of the information of the buckets that contain information for each one of those intersections. And what's interesting about item is that it's not something that we can say blah 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 dot item. It doesn't work like that. Item is the representation in C# of something that you can access with the square bracket notation. So for example, curve intersections, square bracket 0, square bracket 1, square bracket 2, you will see that in a second. But let's take a look at actually what's inside these items. And these items are elements of the type intersection event. So which means that the abstraction of all the information that happened for each one of the cuts is bundled inside another abstraction that is called intersection event. And if we now go to the intersection event class, we can see that finally we have like granular access to all the information that is for each one of the intersections. So for example, whether if it's a point, whether if there's like some overlap information, the actual points for that intersection, and what's going to be most relevant for us, which is the parameters at the curve at which that intersection occurred. Okay, so you're gonna see that there's a lot of like classes and classes going down after we perform that intersection, but it's going to be very easy to unpack. So let me show you how to do that. We're going to go back to our C# script, and the first thing that I would like to notice is that here at the very top, if you probably have this on collapsed, so if you expand this part here, you can see that these using statements are the way in C# to reference namespaces. So basically to say all the information and all the goodness that is contained inside of Rhino.geometry, can you make it available here in my code? And these are the basic ones that we cannot change. So we always have access to these ones. But because we're going to be doing intersections which are a different bucket, like we just saw here, remember this belongs to the namespace rhino.geometry.intersect. We could here in our main code just access that functionality by saying rhino.geometry.intersect. You see, and you see this, you see here this curly bracket notation. That means that it's a namespace. And as we say that, now you can see that we have access to intersection, which is where curve and plane exist. So this would be the way to access the whole tree of dependencies of the namespace without having to reference the namespace. But writing this whole thing is like a little too much. So what I like doing usually is like referencing the namespaces that I'm going to be using in my code. So I'm going to be using here rhinogeometry.intersect. So I want everything that's in this namespace to be available for me. And now I can shorter all of this and just use this kind of accessibility. So how are we going to do this now? So what we're going to do is we're going to create a base plane. We're going to create the cutting plane. The cutting plane has to be horizontal. It has to be, it has to start whatever base point was, so this point here, and it has to be above a certain z height, which I believe we named offset. So the way we're going to start this is we're going to say splitting plane. It's going to be a plane that is going to start. It's going to be horizontal, so it's going to start as world xy. Okay. Then we're going to set the origin of this plane. For example, we're going to set the origin to be base point. Oh, okay. So the point that we had here at the input. And then on top of that, now what we're going to do is we're going to move it up a little bit. We're going to say translate, and we can see from the overloads, we can see that the only overload that we have is a vector to translate this plane on. So we can say, well, let me create a new vector 3D, which is going to be 0, 0, and z is going to be offset. And then move this plane by that offset vertically. If I run this code, everything works, there's no error, so it looks like we're good. Another way of doing this, perhaps a bit more elegant, could have been to just create the plane directly on the origin by saying, for example, actually I'm going to go for that one because I like elegance when writing code. Splitting plane is going to be equal to a new plane, and that is going to be defined by a lot of things. It's going to be defined by, oh, I don't know what's going on, why I can't get, but you can define this based on the origin point and the two vectors. So let me do that. So what is the origin point going to be? It's going to be a new point 3D in space, which is going to be the x coordinate is going to be the same as base point x. The y coordinate is going to be the same as base point y, and then the z coordinate is going to be the same as base point z plus the offset, right? So that's the first parameter, and then the direction of the plane doesn't really matter because we just want it to be horizontal. But for the sake of making it nice, let's just maintain the x and y directions of the vector similar to the world ones. So for the x direction, we can say, let's just use the world. I don't know what's going on with my IDE. Let me just restart this and see. Let's just say vector 3D dot x axis. That's going to be the, and then vector 3D here, the y-axis is going to be equal to the world y-axis. And as we do this, this is probably a bit more elegant, so I'm gonna go with this. I like creating things right with the initial information as opposed to like creating a plane and moving it around, blah blah blah. That's like a little more computationally inefficient. So we have the splitting plane. This works and everything is back to normal. The next thing I'm going to do is I'm going to perform that intersection. Okay, so I'm going to say intersect, which is the element that contains all the intersections. That's the namespace. I'm going to use the intersection class, and I'm going to access all the static methods. So curve, line, curve, plane, whatever. So this is the one that I want, the one that takes a curve, a plane, and a tolerance. So the curve is going to be base arch, so arch curve. Then the plane is going to be this splitting plane that I just created, splitting plane, and the tolerance is going to be some small value. So I'm not going to worry too much about this, just like 0.00 something. What I need to keep in mind though is that I need to store the results of this curve plane intersection as a variable, and that variable is going to be of the type curve intersection. Okay, so where is my, yes, so I'm going to say curve intersections, curve ints is going to be equal to this. And I'm going to just do this so that it reads a little better. Okay, this doesn't work. I wrote something incorrectly. I think this is redundant. I think, yes, because intersection belongs to the intersect namespace is already available in my code. So I think that's how it works. And just for the sake of taking a look at this, I'm going to output this console curve intersections. Let's see how that looks like. Well, I'm not going to here. Yes. So they look like null null. Oh, because it can't convert to a geometry object. So let me just do this. You see, we have two intersection events objects. So here, now remember, the way this worked was curve intersections gives us a curve intersections object that contains items which are of the type intersection event. So this is each one of the intersections. This encapsulates the information for each one of the intersections. So I'm going to try to access those with a for loop. So for int I equals 0, I is less than curve int dot count and I plus plus, and then intersection event I event is going to be equal to this. And remember that I said that items are basically elements that you can access with square bracket notation. So you can see here how with an index I get access to all the intersection event objects which are contained inside of curve intersections. So here I'm going to do I, and then for this guy, you can see that I can already access all that information, overlaps, points, parameters. So what I want is parameter A. So this is where the plane cut the curve for this one particular intersection. I'm going to name this T, okay? And then what I want is for all the intersections, I want to take all the cuts and I want to find those parameters and add them to the list. So basically, this list that I had here before, that was a mock-up, I'm going to put it here. And then once I compute each one of these guys, I'm going to add that parameter to the list so that I keep an ordered list of all the parameters that I have found through those intersections. Is this working? It looks like it's working. And then now I can calculate these splits. So can you tell me, and let's just print this to the console as well. Print t.toString, just to make sure that we see things. So let's print that. I'm going to execute. And you see that the cuts are at 0.1 something something and 1.89 something something. This kind of looks symmetrical as numbers between 0 and 2. That makes me satisfied. It looks like it's working well. So I'm going to say now splits, and then I'm going to cut the curve with these splitting parameters that contains all those parameters. And then the middle, the subcurve is going to be, if we are cutting with a curve with two parameters, we have three curves, and I want to take the one at the center in the middle. So that's going to be splits.1. Let's pipe that out through the console, and let's see. We have this. Oh, this is what I was baking before. Oh, but it's nice. You see how I split this horizontally? So that's looking great. And then, so that's looking great. So compute the subcurve for main arch. So I think that's it, right, for this part. So I'm going to call this something else. I'm going to call sub main arch. Okay. And it's out just because I'm not showing it in the console now. Okay, so with this, I think we're ready now to take both the subcurve that we just generated and the middle arch, subdivide it into points, and join those points with ribs. Okay, let's get to it. But before we go any further, somebody from the chat just reminded me of a method for trimming the curve that is actually much nicer than what we just implemented. So I guess when we were looking at the curve methods, we were not scrolling far enough. We just stop and split. But there's actually a trim method that basically, given an interval or given two parameters, just removes everything that is outside of that interval of parameters from the curve, which probably makes things a bit easier, just so because we now don't really have to, we don't have to create a list of splitting parameters, we don't have to cut the curve in a bunch of splits and then take the one that, so this whole thing here could have been written a bit more elegant if, for example, we just compute the intersection, okay? And then we say, can I take the submain arch is going to be this one, arch curve, okay? And then I'm going to trim this, and I'm going to trim it with two values. But those two values, remember, are found inside of curve in. So we have to dig in a little bit here. So the first one is going to be curve ins. It's going to be the first intersection, okay? Which is going to be parameter A. And then here, curve intersection is going to be 1, okay? So I think this gives us the same result, except that there's an argument missing. Oh no, oh yeah, this should not be, there should be no comma there. It gives us the same, is that true? Let's say console dot submain arch. Let's see if we get that output. Yes, it gives us the same. So you can see this is a little more elegant, but I'm actually happy that we went through this because it also gave us the opportunity to explore a bit more in detail how curve intersections work and how to go in and in. This is more of like a shortcut to me. So I'm just going to keep them both in the final code. Verbose way of doing it. And this is a little more elegant. Is it more elegant? I don't know. It's definitely more concise. So that's for sure. The only thing that I don't like about this is that we're not really checking for, so if, let's say, no, we're not really checking how many if the intersection is successful, if curve ins count is different than 2, so just do like an error component, add runtime message, Grasshopper runtime message level dot error something went wrong with the intersection. Okay, and return. So stop running any more code. Something just didn't work. I mean, ideally, if everything in the previous code works well, if everything is tight, there should be no error with this. There should be no problem with this intersection. But just in case, checking these things out is actually very good practice, just for the sake of clarity. Okay, so where were we? Now what we're going to do is we're going to take the subdomain, the subcurve, and the main arch, we're going to divide it in equal amount of points, and we're going to join those points with with lines, therefore creating the ribs. So how are we going to do this? We're going to do some research as usual, and we're going to say, is there anything that can divide a curve in equal segments? And I think we've done this before in previous videos or live streams or whatever. Here in curve, we have divide by count, which basically says, and we have this one, which is divide by count. How many segments do we want? Whether if we want to include the ends, and it gives us also this additional nice output, which is the actual points. Okay, so I think we probably want to do that right now like this. So I'm going to say here, compute the sub-arch for A. Right. And now here we're going to create the ribs. The ribs are going to be, first of all, we have the base arch. Okay, so that's going to be arch curve, and then this is going to be divide by count, and that's going to be number of ribs, and we want to include the ends. Yes, we do want to include the ends, but we also want to get these points out. Okay, so what that means is that I will have to output those points to some kind of array. So I'm going to call this arch curve points, and I will need to define this beforehand. Arch curve points, and divide by count returns an array of doubles. We could keep those, but we actually don't need them, I think, for anything. What we actually want is the points. So we're just gonna lose the return value that this function is giving us. Can we check if this code has worked? So let me see. I'm going to output through the console. I'm going to output, oh, and we have a problem here. Cannot convert from out. Oh, okay, yep. So I forgot. I declared this as one single point, but this has to be an array of points. Okay, and then you can see here that we have all the points for the main arch, but I made a mistake. It's not the main arch that I want to divide, is the sub-main arch. Okay, so all these guys here. And now what I want to do is I want to say, take the arch in the middle. So where is the arch in the middle? Arch middle curve. Okay, arch middle curve. And then divide by count as well. But I also need to define something before. That's going to be arch curve points, middle arch points, and this is what I want here, and I can output those here as well. What is the error? A variable middle arch points. Have I defined this before? Middle arch, for example, like that here, and then I have this. Oh yeah, middle arch points are the base, like, yes. So I have these ones, and now, for example, just for the sake of it, this is not what we're going to do. List line ribs is going to be equal to a new list, and then for int I equals 0, I is less than the number of points here, and then I plus plus, then just make to ribs, add a new line between point I on this one and point I on the other list of points that we just created. And let me see if this is working. Okay, so this is not working. There's some error. Type expected in 142. What is that? 142 is, I forgot to add this here, so line, and then something is wrong. System array does not contain definition for count. Sorry, this is supposed to be length. You're right. Length. And this, as I run this, now it's working, and it looks like we have the ribs, so that's working great. However, I don't really like, we're not going to be able to, this is not maintainable, because remember, now this is just for half of the first span. And what we need to do is we need to do this very, very programmatically, because we need to take all the curves that we just generated before. We need to take all the curves and all the spans that we have generated, and we need to create these ribs for each one of those spans. So there's a couple ways to do that. So what we can do is, like, we can create a data tree where we go over all the arches that we have generated before, and then we divide by counts, we create those lines, we join them, and then we push them to the final data tree. Or what we can do is, just because all the spans are identical, it's a little cheaper to just go and say, let's just calculate the ribs for the first span, and then let's just clone, let's just copy all those ribs in the spanning direction. So I think that approach might be a little less computationally expensive. So I think that's what we're going to do. So let's go ahead and implement that. Before we go on, let me change a couple things of what I've done so far, because we want to be very rigorous about generating the first family of ribs, the one on the left of the span, and then generating the second family of ribs, the one on the right side of the span, and then use those as the base that we're going to be copying and moving around. Okay, so I'm going to change a little bit of the naming. I'm going to refactor my variables, and here I'm going to say these are going to be the left span ribs. Okay, and so this is going to be, I'm going to have to change this here. This I can take away, and then I will then have to also generate the ones on the right hand side. So what I could do is I could take the curve, the first curve that I have copied and moved here to the right side. I could take that one, subdivided by points, and then like do the ribs. But since those points are actually the exact same ones as the one that I have here, then I can basically just take all those points, move them to the right, or create new points on the right hand side at a distance of span, and then just use those as the base. So for example, arch curve points, this I'm going to refactor this to be on the left, and this arch curve points on the left, and then I can, for example, now I'm going to take it back. I'm going to create a new curve on the right, and I'm going to subdivide that one, and then I'm going to, I'm going to stick to what I said. Okay, so I'm going to say now points arch curve on the right. Okay, and this is going to be equal to a new point array, which is going to have the same amount of points that are currently here on the array of points on the left. So I'm going to create an empty array, points on the right, and then what I'm going to do is, with a for loop, I'm going to populate with this array with copies of the points that are on the array of points of the left arch. This is very hard to explain, but I'm just going to, for those points, I'm just going to increase the x the x coordinate by a distance of d. If you remember the diagram, d is the distance between spans. So with a for loop, and I is less than however many points are here on the left. Okay, and then I plus plus, and then here I'm going to say 0.3d p is going to be equal to a new 0.3d, where I'm going to take this point, the x coordinate, I'm going to take the y and the c coordinate, but then to the x coordinate, to the x coordinate, I'm going to add the distance of d, the distance of the span. And then after I do that, I'm going to say the point in location y in the array of points of the right is going to be equal to that point that I just created. Okay? Let's see. Does that make sense? Is that looking right? So let me run this. I have an error. What have I done? Okay, arch curve points that not exist, 143. So when I was refactoring this one, I have to remember to refactor this, and this also has to be refactored there. Okay, and then you can see that I have here my points on the left. Okay, on the right. That is looking good. And then now that I have the points on the right, I can say, well, let me create a for loop. Let me create an empty array of an empty list of line elements. That's going to be right span ribs. It's going to be a new list of elements. Okay, and then with a for loop, I'm going to go over all of those elements. So that's going to be arch, all the points on the right hand side, and then I plus plus, and then here I'm going to say I'm going to create a line. L is going to be equal to a new line between 2 points. Which 2 points are those going to be? Those are going to be first the first point on the right arch point, so this one, okay? And then the second one is going to be the points in the middle arch. Those were here, middle arch curve points. Also, the one in the same position, the one in position I. And after that, I'm going to take this, and I'm going to add the line that I just created, L, to this array. Let me see if that works. So right span ribs. Okay. All right, it's looking good. Okay, great. So now finally I have my left span ribs and my right span ribs. Okay, I have the two families. So now what I need to do is I just need to create a data tree, and one by one for each one of the spans, start copying and moving all these ribs in sequence. Okay, let's get that going. Let's get to it. So I'm going here to create the ribs data tree, and then very simply I'm just going to go ahead and create, for example, a data tree of line objects here, which I'm going to call rib lines. Okay, and then this is going to be a line object. Okay, and then we need to now create a for loop, which is going to iterate over all the spans that we have. So that's going to be equal to I is less than number of spans, and I plus plus. Okay, and then for each one of the spans, we have to do the same operation two times. We have to take all the ribs on the left. We have to duplicate them, and then we have to displace them. So first of all, I'm going to create a vector 3D, which is going to be a vector that we're going to use to move things in the x direction. So, and this is going to be, for example, v is going to be a new vector 3D, and the x direction is going to be equal to the number of spans that we are, plus the distance d, the distance d, which is the distance between spans, which means that if we're on the first span, I is 0, so we don't move anything, we just copy things in place. If we are on second span, I is 1, so we're going to move things, we're going to move the ribs by distance of 1d, etc., etc. Okay? Now what we can do now is we can say, I'm going to create a list of line objects, and these are going to be left clones. And I'm going to start an empty list here. And here, what we're going to do is we're going to create a for loop where we're going to iterate over all the left spans, all the ribs that we calculated first. We're going to clone them, and then we're going to move them. So that's going to be int j equals 0, j is less than left span ribs dot length count, because it's a list, and then j plus plus, and then here we're going to say line clone is going to be equal to left span ribs dot I. Okay, square brackets I. So because lines are structs, that means that this is a copy. Okay, so what it means is that the variable clone is actually not pointing to the value that is contained here, but this, so clone becomes a copy that of the value that we have in left span ribs, and then if we make modifications to clone, those modifications do not affect the original rib that we have here. Okay, so let me show you. So now that we have clone here, what I can say is, in order to move it, lines don't have the duplicate curve. Lines don't have the duplicate method, the duplicate curve method that we've used before, and because of that, we can't really translate them, and they also don't have a translate. And this is also because, since they are structs, they do not inherit from the geometry-based class, and therefore they don't get all that goodness. So what we need to do is we need to be a bit more manual here, and what we need to do is we need to take both the starting point and the end point of the line, move them with the v vector, and then therefore that becomes the modification of and the translation of the curve of the line. So here what we can say is clone dot from, and that is the point where the line segment starts, and then increment that location by the vector v. And then we can also take clone dot to, which is the end point of this line segment, and do the exact same thing. Increment its coordinates by the coordinates of vector v. Okay, and we have this now. So we have created a copy of clones here, and once we have that, then what we need to do is we need in the rib lines, we can create a data tree. We can create a new branch. So Grasshopper path path equals new Grasshopper, like we did before, and then use I as the index of that path, and then go to rib lines and add range in this case, because we're going to add the whole list at once. Add range, and then take left clones, take the whole list, not just one by one, and then add it at the new path that we just created. If I write this, I don't get any errors. It looks well. So let me create an output here that is going to be called rib lines, for example. And as I do that, I'm going to double click here. I'm going to update, refresh this. I may not want to use the rib lines here then because it's a duplicate name with this. So I'm just going to use, for example, rib axis, for example. And here I'm going to use, I'm going to do that here as well. And then here rib lines is going to be equal to rib axis. I do that and it looks like nothing has happened. What do we have here? Oh, they're empty. Oh yeah, because I forgot to add. You see, we have the empty structure because I forgot to add the clone. I forgot to add the clone to the list of left clones, and therefore we were doing the process, but those lines were going nowhere, and this line remained empty. So we were adding empty lists to the data tree, and I do that, and it doesn't work because I have misspelled something. Yeah, I said clones instead of clone, and I do that, and ooh, something went not very great. I've only moved these 3 lines here. Let's see what happened. It's probably something with so left span ribs that count, line clone, okay, let me take a look at this. Yeah, this is what happens with coding, trying to code things fast. I am in a nested for loop where I'm using I to iterate over the spans, and I'm using J here to iterate over each one of the ribs. And here in left span ribs, I used I, which is the span iterator, as opposed to J, which is the rib iterator. So if I change that to J, now we get this for each one of the lines, but also you guys can see that they're not exactly where they should be. The first one should be here, the second one here, and the third one here, and there's like an offset, and this is because I also made a typo here. This should be I times D. So the number of spans times the distance between spans instead of plus. So I'm going to change this, and I'm going to have it here. Okay, so that is great. And the tree that I'm pulling out of rib lines also looks great because it's branch 0 and then branch 1 and branch 2. They have all these lines. Okay, so that's great. So this is, let me just fill in for the ones on the right. So this is going to be super similar. I'm just going to take this and say right clones is going to be equal. Be careful with copy pasting, okay? So right clones, new list, blah blah blah. This should be right span ribs, blah blah blah, and then clone is going to be right span ribs, clone from clone clue, and then right clones add clone. Okay. If I run this, there's no errors, and then I can copy paste this, and path, new path, blah blah blah. And actually this is redundant because I already have the path, right? So what I want to do is, I want to do here right clones. I want to do this, and then you can see that now we just duplicated the clones on the right, and they have been added to the tree where they should be on. So on branch 0, branch 1, and branch 2. However, okay, I hope you already know me at this point, because this is nice, but it's not as clean as it could be, because what happens now is that I have done this very fast, obviously, and now in branch 0, we have first all the lines, all the ribs on the left, and then continuously, without no separation, we have the ones on the right. So if I needed down the road for some reason to make a distinction between the ones in the left and the ones on the right, I don't know, maybe the sun is hidden from a different the orientation, and I want the louvers on one side to be thicker than the other, whatever. I would have to manually go here, divide the list in two, split them, whatever. So since we're here already, why not create a nicer data tree structure where the ribs on the left and the ribs on the right are much easier to see and are already separated in different branches. So what I'm going to do, but I'm going to do it in a different way. You could argue, well, if you're now creating three branches, 0, 1, 2, because you have three spans, why not create 6 branches? 0, 1, 2, 3, 4, 5, and then the ones that are odd are the ones on the left, and the ones that are even are the ones on the right. We could do that, but that's also not entirely clean. The nice thing about data trees is that the branch allows nesting of levels. So because we have a modular system that has 3 spans, I would like the first level of the data tree, the first number, to tell me which span I am in, and then I would like to add a second level to the branch, a second number that tells me if it's 0, it's the ones on the left. If it's 1, it's the ones on the right, and then have like a kind of like a branching data tree structure, you know. So that's actually super easy to do, because since we already divided that process very cleanly here, what we can say is I can create first for the ribs on the left, I can create a new path. And let me see. So you see how instead of creating I can create a path, an empty path. I can create a path with one index. I can create a path with an array of indices. And then I can create a path copying it from another path. So what I want to do is I want to create an array of indices that represent the levels of my data, of my branch. And I want the first level to be the span that I am in. So that's going to be I. And then the second level to be 0 if it's on the ribs on the left, and then 1 if it's the ribs on the right. So let me create an array here. Okay, int path indices. Okay, and this is going to be equal to a new array of integers with 2 elements, and I believe I can initialize it like this. I believe I can initialize it with the value of I is going to be the first value, and the value of 0 is going to be the second one. Okay, and then as I do that, then I can use that here to specify the index, and then let me see if that works. Did that work? Yes, it worked. You see how now here I have the branch. The branch has the 2 indices. The first one is I, and the second one is hard-coded to 0. And if I keep going, the first one is I, and the second one is hard-coded to 0. So now I can do this. I can do a new one where I say, well, path indices before had this value. Now I want to change that. I don't need to declare it again, but I want to change it and say, okay, path indices now is going to be a new array. I'm going to reset it. I is still going to be I, but then this is going to be number 1 instead. And then I'm also going to reset the path by saying, whatever the path was before, change it to a new path with the new path indices that I just created here. As I run that, check this out. We have 0, 0 here. I'm going to lower the number of ribs so that we can, so 10 ribs only. And then we have here 0, 0, it's span 0. So both have span 0, but then 0 is the left. This is very hard to say. But these are the ones on the left, these are the ones on the right, and then these are the ones on the left, these are the ones on the right. And I actually, can I plug in here this thing where, so that I can see, and look, you guys can see, we have this branching structure. Okay, so this is representing the structure of the data tree. These are the elements, these are the spans, and this is how they separate between left and right. Okay, so I think this data structure is much cleaner as an output, and whoever was to take this data and start working with it could operate much cleanly with this data structure here. So I find that solution much better and much more pro. So I'm just gonna go for that. Okay. Okay. So that was a lot. But I think we're ready now. I mean, we have the whole, we have the whole, we have basically have the whole building already. So now in number of spans, and we have the whole building written in C# script, and then we can just modify the width, we can modify the height of the elements. Oh, this is actually quite cool. Huh. And then we can make them, the spans, we can make them wider. This is like the Madrid airport almost. This is kind of cool. And now what we need to do is, in order to complete this, what we need to do is we need to create is, for example, if this was a competition, we will need to create solid object surfaces so that we could render this, as opposed to the lines that we're doing here, which could be used, for example, as an axis for the structures. So let's go ahead and create the variable thickness beams for the arches and create the tubular pipes for the lines. Okay, let's do it. Before we start coding, as usual, it's very important to to refresh our thing, to refresh things in our head and to have a clear picture of where we want to go. So let me refresh what we did in last video. We had because the beams had a variable section, so the section was much larger here close to the base than it was all the way up there in the top, because there's more stresses. There are more stresses coming near the base. So we wanted to mimic that. So, and we came up with a very simple numerical rule to figure that out. But what we're going to do here is, because it's going to take quite some code to put this together in C#, what I want to do is I want to do first a very simple example where we just take the curve, we subdivide it into all those sections in all the planes, perpendicular frames, and then we just place there a very simple section, like for example a circle, and then we create the sweep. We create the sweep with that circle, curve, just for the sake of learning how to create that surface and that B-rep. And then once we got that under control, then we will figure out how to actually turn those circles into rectangles, and how to have those rectangles have a dimension that is proportional to how far away they are from the base. Okay, so let's do this in a very stepwise manner. Let's do the simple part first, which is the sweep, and then let's implement after that the numerical rule to have the rectangles vary in the section. So let's get started. We're going to add some comments here. This is really good practice. Create main arch sweep B-rep. And what I'm going to do is, the first thing that we're going to do is we're going to take the arch, the curve that we created before, and then we're going to subdivide it in perpendicular frames. How are we going to do that? Well, first let me figure out where that curve was. Arch curve was the base, so I'm going to bring this here. That was the name. And then what we need to do is we need to subdivide this into perpendicular frames. So there's got to be something in Rhino common, and I was looking it up before, and we have the curve subdivide get perpendicular frames method, which gives me a collection of perpendicular frames along the curve. So that's probably going to work. So what I'm going to do is, and the return type is going to be a bunch of planes, which is exactly what I want. So let me go back here and let's say plane perpendicular frames main arch. That's going to be equal to arch curve dot get perpendicular frames. Okay, and what this function needs is an I enumerable, which is just a way of saying that something that is a list-like element, like an array or a list, of the parameters. So it kind of sucks because I can't really tell it. Just give me subdivide this in 30 different frames. So I need to give it the parameters at which I want those perpendicular frames. So we need to do something before. What we need to do is we need to figure out for this curve, we need to subdivide it in however many elements and then get the parameters of the curve at those subdivisions. So I'm going to put this on hold here before, and then what I'm going to do is I'm going to rely on this other method, curve divide by count. And if you see, this takes how many segments and whether if I want to include the ends or not. And the return type is an array of doubles that are the curve parameters at those divisions points. So what this does is, given the curve and given how many segments I want to divide, it gives me the numerical values of those parameters along the curve. So this sounds really useful. So I'm going to say create a double array of main arch, for example, subdivision parameters. The names of these variables are ridiculously long. Please don't do this at home like this, okay? So what I'm going to do is arch curve, and I'm going to say divide by count. And here, how many segments are we going to take? I don't know. We could have this as an input, so we could let the user decide, but we also don't want the user to be able to input like parameters that we don't like, that they're too low for perhaps. So I think for this one, I'm just gonna hard code in a number. That's not great practice in general, but I also don't want the user to be able to input a number that would not work. So I'm just gonna go, for example, for 30, which I believe is what we did in the vanilla exercise. And then I want to include the ends, that is true. And this way, I will get all these parameters. Now that we have that, I can use these parameters here. And then let me just output all these planes to see if they make any sense whatsoever. I'm going to run this, and it looks good. It looks like these planes are more or less evenly distributed, and I like that there is one exactly at the center of the curve because I want that kind of symmetry. I want this to be exactly the size of D2, just as we had in the diagram. So things are looking good. Okay, now I'm going to use these planes to generate circles. For example, how am I going to do this? I'm going to create a circle array of sections, and this is going to have the same size as the number of planes that we just created. Okay, and then I'm going to go ahead, and with a for loop, I'm just going to create as many circles as frames that we had. So this is going to be equal to sections dot length, and then I++, and then here I'm going to say for each one of the planes, so plane PL, give me the plane that I want. Okay, and then circle C is going to be equal to a new circle that I'm going to create with the base plane and the radius. So plane and then the radius, I think I'm going to use lowercase w, which I think is one of the input values, but this is going to be a placeholder. I will change this later. And then sections I is going to be equal to that circle that I just created. What does that mean? Is that working? Let me see if I can output all these sections. Okay, and it looks good. I just created an array of circles, one per plane. Okay, and I think we should be good now to create the sweep so that we can see how that works. As usual, it's a very good thing to go to documentation. So we can see here that sweep is not an operation, it's actually a class. So what that means is that sweep one rail, it's an utility class. So you cannot really create a surface by just saying surface dot sweep one rail. There's actually a full class that is dedicated to handling how sweep rails are created. So for example, if we go to the constructor, as we saw before, there is a tiny example here of how to do that. So it looks like, this is the first time I'm doing it myself. It looks like we have to create a new instance of sweep one rail, then we have to define some parameters, okay? And then once those parameters are defined, then we can perform the sweep, inputting the rail curve that we want to use and those cross sections, okay? So I'm going to copy paste this here. I'm going to copy this in my code so that I can use as a template. Okay, and I'm going to rewrite it so that it looks more like, so that it uses the variables and all the stuff that I've been working with. So how are we going to start? So I'm going to say sweep one rail, sweep operation is going to be equal to a new sweep one rail object. Okay. Then the next thing is I'm going to set some. I'm going to call this sweep. Then I'm going to set some variables. So for example, angle tolerance in radians. I don't know what this really means. We could look it up, but maybe do we have access to the doc property? Yes, we do have access to the document property, so we're going to just keep it like that. Sweep, is this going to be a closed sweep? That's going to be false. Is this going to be a sweep tolerance? Is going to use also the document tolerance mode, and then sweep is going to be set road like top. I have no idea what this means. We could look it up, but I'm just going to copy it. If you're interested in really tweaking this, you are more than welcome to look at the documentation. And then now what's interesting is that we want to do perform sweep. Okay, so sweep, perform sweep, and it doesn't look like perform sweep on its own exists anymore or is accessible to us. Let's take a look at that. Perform sweep curve, and this is missing the documentation. Perform sweep rebuild, perform sweep refit. Is supported in Rhino for Windows 625? 625. Am I on Rhino 625? Where is Rhino 621? So maybe I don't have access to that functionality yet. Is that possible? I don't know. Perform sweep. Let's just try. Yeah, because it actually shows up. So maybe it was just not showing up on the panel, which is kind of weird. But anyway, so let's take the arch curve as the rail curve, and the cross sections are going to be the sections. Okay, and this is going to return an array of B reps. So an array of B reps. So that's going to be, what am I going to call this? Arch, main arch surfaces, for example. And then here, I'm going to output that, see if it works. Okay, it is not working. So something is going. The best overloaded sweep rail preferred has some invalid arguments. Cannot convert from Rhino geometry circle to Rhino geometry curve. Okay. Okay, let me take a look at this. Yes, so the problem that we were hitting is that Rhino was not able to accept here, was not able to accept an array of circles because it needs an array or a list of curves. And it just so happens that even for us, circles can be thought as curves, but the circle structure is actually is actually a numerical structure that doesn't inherit from geometry base, or it doesn't belong to the curve class. So the conversion is not automatically. So the only thing that we need to do is that we can still work with circles and create circles, but before we store them in this array, we have to turn them into NURBS curves. So the first thing that we can do is like we can change the type of the sections array, and instead of being an array of circles, it's going to be an array of curves. So that's one thing. And then the other thing is here. So if we run this, you see that in line 203, we cannot save a circle inside of a curve array. The only thing that we need to do is we need to take the circle, and before we save it into this array, we need to turn it into a NURBS curves. So we can use the method called toNURBS curves, convert it, and then save it into that array. As we do that, I can now click here, and I can see that nothing shows up. But if I now take main arches and I output it in the console output, you can see that I now have my pipe that has been swept over the rail, which is the base arch here. Okay, all right. So I think we're good. I'm going to remove all this nasty code here. So I think we're good now for as how to create a sweep, and I think we're in a good position now to start looking at how to instead of using plain circles, how to create rectangles and how to change the dimensions. So I think the first thing we're going to do is like right away, we're just going to create rectangles here. So we're going to substitute here. Instead of doing circles, okay, I'm going to say rectangle 3D. I believe R is going to be equal to a new rectangle 3D. And then this is going to take a plane. So that's going to be PL. And then the width, which I believe, let me take a look at the diagram. I believe the width was W. And we're just going to use, for all of them, we're just going to use D1. And we will take a look at how to change that programmatically. So now the width is going to be W, which was one of the inputs, and D1, which was another one of the inputs. And then here, we're going to take the rectangle and we're going to turn it into a NURBS curve as well. Before we and then I'm running this, but I'm not seeing anything. Oh, because I did. Okay, and we can see that we have the arch, but the arch is not entirely what we would want to. First of all, for us, the width and the height are flipped. That's one thing. But also, you can see that the arch is here. And because we're using width and height, the rectangle is not applying that width and that height at the center. It's applying it offset. So it's taking the center, the line is taking it as the corner of the section. So what that means is that I'm going to have to work a little bit with my inputs, and I'm going to have to look. Let me look at other ways of creating rectangles. So if we look at the overloads, of what a rectangle accepts, you can see that it takes a plane and then two numbers, width and height, but it can also take two intervals for the width and the height, as well as 2 points in the corner. The points are going to be really messy to do, but if we use intervals, we can create an interval that goes from minus half the width to plus half the width, and to minus half the height and plus half the height, and therefore we would have the rectangle centered around the rail curve. So let's do that. So I'm going to say interval width is going to be a new interval that is going to go from minus 0.5 times width and 0.5 times width. That's one thing. Then the interval for height is going to be minus blah 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 d1 plus blah 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 d1, and then I'm going to use these two. I'm going to use PL, width and height. And as I do this, let's cross fingers. Yay! You guys can see that now the section is perfectly centered around the rail, but width and height are flipped. So I don't know whether if to change the numbers or to change the where these guys go. I'm just going to do D1 and D1 and W and W, and that's how I'm going to switch things around. Okay, and so that's looking great. Great. So we're almost there. Now the only thing that we need to do is we need to figure out the numerical rule to make the sections decrease as we go up. Okay, and that's also going to be super easy, as opposed to how we did in vanilla Grasshopper. That was a little convoluted, but here it's just going to be a couple of multiplications and divisions. Let's take a look at that. Just a refresher, what we're going to do to implement that rule is we're going to implement a rule where for each one of the sections, so all the way from the bottom to the top, for each one of the sections, we're going to compute in relative terms, so from 0 to 1, how far off the center of each one of those sections is from the base plane where the building is sitting. So if the plane is at the bottom, then the value of that proportional distance is 0. If the plane is all the way at the top, then the value is 1. And then all the planes in between have proportional values 0.1, 0.2, 0.3, etc. Okay? And then we're going to use that numerical value to decrease the section by that factor. So we're going to calculate how big the section is in the bottom, how big it is in the top. We're going to calculate the difference in section, so how much it decreases. And then we're going to multiply that value by 0, 0.1, 0.2, 0.3 to start decreasing the value of the section over the height. Okay? So this sounds much more difficult to explain than to do. So for example, let's say here, where I'm going to calculate double section difference is going to be equal to D1 minus D2. So that is how much the section decreases from the bottom to the top. Okay? And now what I'm going to do also is I'm going to here for each plane, I'm going to calculate something that I'm going to call the normalized height. Okay, so that is going to be from 0 to 1, how far off this is from the ground. And that is going to be where that's going to be the C height of the base point. So where the base point, so that's going to be the C height of this one, and the C height of the where the plane is right now. So plane dot origin z minus base. So the C let me say this again. The C coordinate of the origin of the plane minus the C coordinate of the base point. So that's going to be how far the center of this plane is from the ground. But it's going to be in absolute terms. It's going to be in whatever units we're working with. But to make it proportional, what I want to know is, what I want to do is to take all of this and divide it by the full height of the building, which, if I remember correctly, is h. So what that means is that if because h is, I don't know, whatever, 10 meters, if the height of this point is 10 meters over the ground, then this point is going to have a normalized height of 1. But if this point is 0 over the ground, then its normalized height is also going to be 0. Now once we have this, we can compute. How much do we have to decrease the section. So double is going to be the section, the new section height is going to be equal to d1, so the base, minus the section difference, so how much is the difference, times this normalized height. Can you guys see this? So we start with the base, and we start, because this becomes greater and greater and greater as we go up in the arch. Then when this hits 1, which is at the very top, the section is d minus the difference, which is going to be d2. Okay? And then we use that now as new section height. Okay? And I think that's it. Is that true? We have an arch. The arch looks like here is much higher than this here. And here is 0.40, here is 0.15. Let's bake this and see if it's true. So I'm going to bake this, and then, oh no, actually, sorry, let me bake. What did I bake? What did I just bake? Okay, I don't know what I baked. Let me bake the console output. So the console output is this one. Let me bake it. So now we have the surface here. And I'm going to do this, and then I'm going to do distance, and that's going to be from here to here, and that's 0.40. That's what we had here. And if I go all the way to the top, I'm not sure which one of this is the section. So I think it's this one. So distance from here to here, and you can see that the distance in the C is 0.15. So I think we got it. Nice. I think we got it. Okay. So awesome. So now we have the arch with the varying thickness. Okay. Very clean. Very parametric. Very procedural. We can tweak these things. So now this is much thicker on the top, and this is close to 0 in the bottom. That's also a kind of cool design, huh? With that, now we're ready to take this B-rep and to start replicating it. Down in the spanning direction. Okay, using data trees. Shall we take a look at that? Okay, let's get to it. Before we move on, I want to notice one thing. The return type of perform sweep, it's not one B-rep, it's actually an array of B-reps, because sometimes, depending on the parameters, if things are not perfectly aligned, etc., you may actually get multiple surfaces as opposed to one as the result of the sweep process. So that's why the return type is an array. But since here the process is much more controlled, and we've taken good care of making everything programmatic and tight, it's probably going to always be just one B-rep. So I want to make sure that before I start cloning this and moving them around, that instead of doing that with an array, I do it with the one single B-rep that is the good result of our operation. So I'm just going to either take this, or I'm just going to make it more verbose. Main arch B-rep. Okay, and that's going to be main arch surfaces, the first element of the list. Okay, and this is the one that I will output here, and you're going to notice something probably as I click run. This is going to go from, you see, instead of going from a 2D, a tree with a path with two levels, it just becomes one, because instead of outputting an array, we are outputting one single element. So Grasshopper processes that in a different way. which is a bit cleaner. And then now create data tree of B rep arches. Okay, so first I'm going to create myself an output here. So that's going to be base arch curves, and I'm going to say base arch B reps. Okay, so that's going to be one. I'm going to remove this stuff here. It's getting a little clogged, and I'm going to go all the way down here and say, as usual, let's start a data tree. Let's start a data tree of B-rep elements. Okay, of B-rep elements, and I'm going to call this base arch, base arch. Why do I always get stuck doing this? Base arch B reps, for example. B reps, but that's the same name yeah, that's the same name. Base arch surfaces, for example. And this is going to be a new data tree. Okay, and this is going to be of the type B-rep. And then here, I'm going to iterate over all the spans. And then I'm going to take the B-rep, and I'm going to take main arch B-rep, and I'm going to duplicate it. I'm going to duplicate the B-rep. Okay, so to create a copy of it, and then I'm going to move it, and then I'm going to move it in X, an amount equal to I times D, which is the width of each span. And then I'm going to create a new path, a new grasshopper path, which is going to be equal to a new grasshopper path with I, and then to this data tree, I'm going to add this B-rep that I just created at the path that I just designed. And all the way at the very end, I'm going to output here. I'm going to say base arch B-reps is going to be equal to this data tree that I just generated right now. And that failed. Oh yeah, sorry, because I forgot that this has to be XYZ. So that's going to be 0 and 0. Yes. And as I do this, things work well, and it looks like I have all those arches. So this one is duplicate. So I'm going to remove the console. I'm going to stop outputting that, and I'm going to copy these so that I have a dedicated one. Exactly. So it looks like we're good, except, you see, except that I need to do, just like I did before, I need to add one more element to the span because we have one more arch than spans. So that's just going to be as easy as number of spans plus 1 here. Okay, we got this, and okay, so I think with this, we are more than ready now to go ahead and then just I know we have to do the arches in the middle. Okay, so we're going to do the same process but with the arches in the middle. Okay, cool. I'm going to copy everything manually just because I don't want to copy paste things and forget to rename something and then spend half an hour debugging it. So if you don't want to get bored, just speed through this part because I'm basically going to copy paste everything and then just do like small tweaks. So I'm going to create middle arch sweep B rep. So that's going to be double middle arch subparameters are going to be equal to what is the name of the middle curve? It was arch middle curve. Okay, so here dot divide by count, and I'm going to use the same number, true, and then I'm going to create an array of planes. This is going to be perpendicular, frame, middle arch, and this is going to be equal to arch middle curve dot get perpendicular frames. Boom, boom, boom. Get perpendicular frames, and main arch subparameters, middle arch subparameters, and then curve, another array of sections, middle is going to be equal to a new curve array equal in amounts of this many elements dot length. Okay, and then double section. I'm just going to recycle this. You know what? I'm actually going to recycle some of this. So this can be sections is going to be equal to a new array. Section difference is going to be equal to md1 minus md2. So I'm just going to reuse these variables so that I don't have to declare them again. And then this for loop is going to be exactly the same thing because I'm going over sections. And then plane PL is going to be equal to perpendicular frame middle arch, and then this is going to be the exact same thing. The normalized height is going to be the same. New section height is going to be also the same because it's going to be new section and section difference. I'm using the same numbers. Width is going to be equal to, you see, I end up copy pasting. I should start like listening more to what I say. You see here the danger. I should have, and I have to remember to make this MW, and then the rectangle. These two things are going to be the same. So rectangle R, new rectangle PL, PL, and this looks good to me. And here, because I already have a sweep class that has all the parameters and all the configuration that I used, I can reuse this same sweep, variable to perform the sweep. And this I'm going to use arch middle curve as the rail, and then the section I'm going to use sections, and then I'm going to store that in an array. brep middle arch surfaces is going to be equal to the result of this, and brep is going to be equal to middle arch brep. It's going to be equal to this thing here, to the first element of the list. And let's output it in the console so that we know if it's working correctly, and it looks good to me. So right now this is this is looking very large. Okay, so if I bake this, it's probably not. It's probably way too large. So distance, this is 0.38. That is very odd. You see, there's probably some copy pasting that I should not have done here. 0.358. Nope, that's not good. And distance here is going to be right. It's going to be equal to 0.235. Yeah, so something is not working here. So let me take a look at what that is. It's something with the heights. So section difference is MD1, MD2. Oh, you see the copy pasting. You see, I was telling you, I'm subtracting from D1 as opposed to MD1. I knew it. So let me bake this again and make sure that it's correct. So distance here is now 0.85. Did I measure this correctly? In the Z 0.85, that's not correct. And this distance should be this distance is 0.208. Nope, still not working. Okay, so MD2. Okay, yeah, the height, because the height is not anymore the origin Z and the base point. The height difference is, yeah, the normalized height difference has a different rule now. The normalized height difference is different. So we have to figure out what is H for the main arches, what is full H, and what is the difference between this point and this point. So that is where things are not, yeah. So you see, copy pasting, it never works. Okay, so let's take a look at this. So we have here at the beginning, we made this list of middle arch points. Okay, so this middle arch points is an array that has is a list that has the 3 points that we use to create the middle arch. So the first one is the one that has or we could do this numerically. Let's do this numerically. So let's say double arch base is going to be equal to base point, the Z height of base point, plus, I believe it was, what was it? It was H1. Okay, so plus H1, double arch top was base point plus height of the arch plus H2. And then double arch height is going to be equal to these two. It's going to be equal to the difference between these two. This minus arch base. Okay. So that's there. And now this, instead of base point Z, this is going to be arch base, and this is going to be the height of the arch. And as I do this, I don't know, things have not changed a lot visually, but I'm still going to bake this to see. Oh, sorry, I've been doing all of this. Oh, I've been doing all of this. Sorry, I've been doing all of this in the diagram. So yes, what I just wrote was I added these 3 lines here where I was computing arch base, arch top, and arch height. So the height of the middle arch, and then how high the base of the middle arch was, and how high the top of the middle arch was. And the height is the difference between those two. And then I replaced here. Now the base is this new value, arch base, and the total height of the arch is this one. Let's see if this works. So I'm going to calculate this distance, and this is 0.25. Now we're talking. And here on the right, this is 0.1 millimeters. So, okay. So this is what happens with mindless copy pasting. Hope you guys never do it, just like I did. Okay, and now let's write a data tree here, where we create a data tree, create a vrep middle arches. So data tree vrep middle arch surfaces is going to be equal to this stuff here. And then I'm going to copy this. It's going to be vrep. So number of spans, we don't want to do +1 right now. Vrep is going to be equal to main arch vrep. No. Middle arch vrep, we're going to duplicate this. We're going to translate it 1 times d. Path is going to be good. And then to middle arch surfaces, we're going to add this vrep here. This gives me an error, which is, what is it? 250, line 251. I can, oh yeah, the name is already in scope. So middle arch surfaces, middle arch surfs, for example, here. We're going to change that. Yes, I was just duplicating the name here with the data tree as well. And let's create an output here, middle arch curves, middle arch vreps. Okay, we need to close this so that it updates. And middle arch vreps is going to be equal to the data tree that we just created. Okay, and is that true? It is. It looks like it's true. So we now have these the middle arch vreps. They're full solids, and yep. Okay, so we're good to go. So it sounds like the only thing that is left is just to do the piping. So that's going to be hopefully super simple. Okay, let's get to it. Now, as I was checking the Rhino common documentation to find the piping methods, I run into vrep create pipe, but it strikes me. So this is what we would have probably used in vanilla Grasshopper to create a pipe around the lines, and I think that's what we did in the previous video. But it strikes me that this operation is super complex and it's going to be probably computationally super expensive, way more than we need for just simply extruding a circle along a simple line. Create pipe is probably great if you have a curve that has a lot of twist and a lot of torsion, but for us, in such a simpler scenario, I think this is probably an overkill, and what we probably want to do is find something simpler, like for example, surface create extrusion. So create an extrusion as from just a simple profile curve and a direction vector, because at the end of the day what we have is a line, and a line is almost equal to a vector between the 2 points, the start and the end point. So this approach is probably going to be much simpler to implement, and it's probably going to be also much more lightweight computationally to do. So we're going to do as we did before. We're going to generate all the surfaces for the left ribs and the right ribs, and then we're going to clone them. Along the spanning direction. And actually, we're going to do that by going back into the code and going to where we were creating the ribs. So here, the left span ribs as lines and the right span ribs as lines. And we're going to take advantage of the fact that here we're already looping and generating these lines, etc. And we're going to insert some code here to at the same time as we are creating the lines for the ribs, to also create the surfaces, and then just like do everything in one go, you know. And we may actually take advantage of this code here as well to make things a little cleaner. And in order to do this in a much cleaner way, what I'm actually going to do is I'm going to create my own function. It's going to be a function that I'm going to call it, for example, something like pipe from line. And given a line and given the radius of the pipe, I want that function to return a surface that is going to be that extrusion. So in order to do that, I'm going to go all the way down here, and I'm going to create a new function. That function is going to return a surface object, so that's going to be surface. I'm going to give it a name, so surface so for example, pipe from line, and then the inputs that these are going to take is going to be a line object, is going to be a double, the radius, and then that's it. I don't need anything else. Okay, so how is that going to work? Well, first of all, if what I'm going to end up using is surface extrusion, okay, so what I need to do is I will end up creating something like surface extrusion, blah, 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 and then this will need the curve profile, so a circle, and then it's going to require the direction extrusion. But I don't have those yet. I have to create them. So the first thing I need to do is I need to create a vector, direction vector, and then the circle, I need to create it. I need to create a circle that is placed at the beginning of the line and whose normal is also in the direction of the line. So let me put a hole to this one. And first of all, let's say vector 3D direction is going to be equal to a vector that is formed by the point at the end of the line, so line 2, minus the point at the beginning of the line, so line from. That vector is going to be a vector that is going to be in the direction of the line and is going to have the length of this line. And the circle, we first need a plane located at the beginning of the, we need a plane that is going to be located at the beginning of the line, at line from, and whose normal is going to be perpendicular to this. So let me say plane base plane, or PL, is going to be equal to a new plane. And you see, we can create a plane from an origin and a normal. So we do have the origin, so that's going to be line from, and we also have the normal, is this vector, this direction vector that we just created. So direction. Okay, then the next thing is going to be circle C is going to be equal to a new circle based on that plane that we just created, so PL, and with a radius of the value that that is coming from the function, so radius. And then remember that we can't work with circles directly when we do NURBS operations, so we need to convert the circle into a curve. So that's going to be curve CRV is going to be equal to C, the circle that we created before, converted into a NURBS curve. I think now we're ready to go for this guy. So now the surface is going to be create extrusion. We have the curve profile, so that's going to be CRV, and we have the direction vector. So that is direction. And I think that's it. So this is the object that we want to return, SRF, surface. Okay, good. So let's go back now here. Let's go back to, and I'm going to copy this name because I'm going to forget it, of course. Here where we were creating the base riffs, we probably want to create here a list of surface objects called the left span surfaces. New list, blah, blah, blah. And here, and now I'm going to rewrite this a little. I'm going to put this here. I'm going to write this a little. So I'm going to say line L is going to be equal to this new line that we created here. Okay, and then I'm going to add the line to the list. Okay, so that's fine. And then now I'm going to say surface SRF is going to be equal to pipe from line, that function that I just created myself, and line, I'm going to use L, which I already have, and radius is going to be, what is it going to be? Pipe radius, yes. So we have it as an input here. So that is going to be, where is this? Pipe from line, pipe radius, okay, and then after I create that surface, I want to add it to this list left span surfaces. So add dot srf. Okay, do I run this? It doesn't work. Something is broken. 146 here. Oh yeah, I forgot this here, 146. Okay. And we don't see anything here yet because we're not outputting it yet. So let me use the console to see if that, so console equals left span surfaces, all these guys. So I'm going to output there and boom, turns out we are creating all those surfaces and you can see all these pipes out there. So that's great. It's looking nice. And what is the next thing to do? So I'm going to remove this. I'm going to do the same thing for the right spans. So here I'm going to create another list of surfaces, and this is going to be right span surfaces. And here I'm going to create a surface S is going to be equal to pipe from line L and the radius, and then right span surfaces at S. Let me output this to the console to see if it works. Here, there you go, and then it works. We have them here, and now we're just going to use the data trees. So we're going to take advantage of all this for looping that is going on here to also create a data tree of surfaces, and we're going to apply the exact same logic that we did before. We're going to have, this tree is going to have two levels. The first one is going to be the module, so which span are we in, and the second level is going to be 0 for the left pipes and 1 for the right pipes. So let me create here a data tree of surface objects. So rib surfaces, new data tree. Okay, and then surface, and then here we have the vector, left clones, we have the clones. So here I'm going to create surface left surf clones, new list, blah blah blah, surface. Okay, and then here we have the same number of lines and pipes, so we can reuse this for loop. Here we are working with the lines, but now here we're going to say surface clone S is going to be equal to wait. So wait. Yeah, it's going to be equal to left span surfaces. It's going to be equal to left span surfaces I, and that here. Something is not working. Okay, surface source, the original one is going to be this one. Okay. Now, can we take source and can we duplicate it? Can we duplicate? Yes. So duplicate shallow. Yes. So can we duplicate this? Okay. And then as we do that, we're going to say clone s dot translate, and we're going to translate it with vector v, vector that we just calculated before, and then we're going to add this to left surface clones at clone s. Okay. Something is not working. Cannot implicitly convert type geometry base to Rhino geometry surface. 191. So we're not going to be able to duplicate this. So let's try duplicate shallow. Now, so I think the way to fix this is to just say we can duplicate it, but then we're going to have to cast it again into a surface object. Yes. So this method was returning a geometry-based object, which we cannot store on a surface object. We have to explicitly cast it back to the surface type. Okay, and since we're here now, And so surface clone is here, left surface clone, so path indices, rev axis, so rev to rev surfaces, I can add a range, which is going to be the left surface clones path. Okay, this works. So let me rev lines, let me here on rev surfaces add an output, and here, where is it? Rev surfaces is going to be equal to where did I have this? Where did I have this? Rev surfaces here. I'm going to output this, and it looks like, okay, so let me turn this off. Let me copy this here. Let me turn this off again. It looks like it's not working, and that I am duplicating all of these guys. This is probably, I think this is probably similar to what we did before. There's some problem with an I and the J. Yes, so here, instead of I, this is J here. Okay, so that's great. Now we have all the elements on the left, and we are now just going to finish that off with the elements on the right. So there is surface left clones. So here I'm going to copy this, and I'm going to call it right surface clones, right span ribs, right span ribs, so blah blah blah. And then here, same thing, source. This is going to be right span surfaces, J clone, surface duplicate clone, and then right surfaces clones add there. And here we're going to right surfaces clones here. And ta-da! And it looks like everything is working correctly. And it looks like we have everything. These are the B reps. And these are the curves. These are the B reps as well. And these are the surfaces. So it looks like everything is working. So let me just do some baking so that we can see if everything works. Da-da-da, and then bake this, yes, and bake this, da-da-da, and then we're going to turn this off, and we're going to do a little bit of better shading. Oh, rendered, yes. All right, and here we go. Doo-doo-doo. Finally, yay, that was a lot, okay? Okay. Doo-doo-doo, yay, fireworks, yay. All right, oof. Ay. Okay, so here we are. So this is the modeling of the Calatrava's umbracal building in Valencia, done in purely C# scripting. It took us a little time to get this together. It may seem a little tedious, but I think this exercise was incredible in that we were able to touch upon a lot of interesting topics and a lot of for example, how to create sweeps, how to manipulate data trees, how to customize the paths, how to rethink, for example, pipes, and for a very simple situation, just conceive them as a very simple extrusion. So I think that was a very good exercise, and I hope you guys could see the very, very fine level of detail and control that we get when we start customizing and writing these applications on our own. I can't really tell, but I'm also fairly confident that this component with its 300 milliseconds execution time is probably much more performative than the same code running on vanilla Grasshopper. So that's also an advantage. And very often it has happened to me in professional life when I have like very really complicated models that have a lot of different geometry, and I need to do a lot of operations for like 3D printing and slicing and that kind of stuff. Writing these things in C# definitely pays off. So I this exercise could use a lot of things. It could use a little bit of cleaning up and optimization of the code. It could use like introducing more variables. So for example, instead of using a square section, we could have done a W section, like in the original model, in the original building. We could have trimmed the pipes so that they actually land exactly on the side of the beam, as opposed to getting into the beam. So like they do here. So if we zoom in, so here, if we zoom in, you can see how these pipes actually get into the beam. We could have worked with some intersections and to make that a bit cleaner. You see how this, for example, is not very clean. We are starting the rifts exactly at the beginning of this curve. So this is actually not a very realistic joint in the real world for execution. So perhaps like adding some kind of offset here, like we did here, would have been an interesting thing to do. But I'm going to leave all those additions to you, the viewer. If you want to pimp this exercise up, or like maybe add geometry even underneath the building, add people walking around, or like make it more fancy, or now maybe you wanna design the structure of the concrete beams that are supporting this platform. It's totally up to you. Remember that we are always open to contributions. So if you make something cool, or if you extend this exercise much further, feel free to reach out or to do a pull request on the GitHub repo and submit your code if you want to share it with the world. You can also share it with us on the Discord channel. And if you were interested in how the process that I followed to actually figure out, because I did not prepare this video at all, if you want to interested in the process that I followed to figure out how to tell the story and build this here with you, make sure you check the live streams that I used to build this, and that can probably help you even better understand how to get to know Rhino Common better. Okay, so until that, we're going to be doing more of this. So feel free to like this video, to subscribe to the channel if you want to learn more about computational design, and see you in the next video.